Okay, so you want to own a nuclear power plant. Split the atom, boil some water, generate massive amounts of zero-carbon electricity, and watch the cash roll in every time someone turns on their lights. It sounds like the ultimate energy monopoly. You hold the key to the most energy-dense material in the known universe. You do not have to worry about the sun going down or the wind stopping. You possess the absolute pinnacle of human engineering. Here is the strange part. Almost nobody wants to build one. In the United States, exactly 2 new nuclear reactors have been built from scratch and brought online in the last 30 years. Both of them are at the exact same facility in Georgia. Not because nuclear power stopped being necessary, but because it became one of the most financially catastrophic undertakings in modern industrial history. By the end of this video, you will know exactly why owning a nuclear plant is less about physics and more about navigating an economic nightmare. How the cheapest fuel on Earth is trapped inside the most expensive building on Earth. Why the very thing that makes nuclear power so perfectly reliable is exactly what makes it lose money in modern energy markets. And why the business that could actually save the planet from climate change is, more often than not, structurally incapable of turning a profit. Let us start with what it actually costs to get in. Building a nuclear power plant is not like building a gas station, and it is not even like building an oil refinery. You do not just buy some land, order some steel, and pour some concrete. You are building a localized fortress designed to safely contain the sustained power of a star while simultaneously being able to withstand a direct strike from a fully loaded commercial airliner, a 9.0 magnitude earthquake, and a total loss of all external power, all at the exact same time. The industry uses a financial term called overnight cost. This is the hypothetical number of what the plant would cost if you could magically build the entire thing in a single night without paying a single cent of interest on your loans. The overnight cost of a modern gigawatt-scale reactor is estimated at around $6 to $9 billion. But you cannot build it in a night. It takes a minimum of a decade. And that is where the math utterly destroys you. When Southern Company started building Plant Vogtle Units 3 and 4 in Georgia in 2009, the estimated total cost was $14 billion. And the 2 reactors were supposed to be done by 2016 and 2017. They actually finished in 2023 and 2024. The final price tag was roughly $35 billion. That is over $20 billion over budget and 7 years late. This is not some rare anomaly. It is the absolute standard for the Western nuclear industry in the 21st century. The primary cost of a nuclear plant is not the concrete or the uranium. It is the cost of capital. The interest you pay on the billions of dollars you have to borrow to build the thing compounds every single day the project is delayed. If your massive concrete pour is halted for 6 months because the Nuclear Regulatory Commission needs to review a sudden design change in the rebar layout, you are paying millions of dollars a week in interest and carrying costs for a plant that is producing exactly 0 electricity. You are bleeding cash just standing still. And the regulations governing that standstill are staggering. The entire industry operates under a principle called ALARA, which stands for as low as reasonably achievable, referring to radiation exposure and risk. But what is considered reasonable shifts, and the standards are uniquely punishing. Every single piece of equipment, every valve, every foot of electrical cable, every batch of concrete must be certified nuclear grade. A standard commercial industrial valve might cost a few $100s. The exact same valve, physically identical, but certified for a nuclear plant with the required paper trail of metallurgical origins, extreme stress testing, and quality assurance can cost tens of thousands of dollars. You are not paying for the metal. You are paying for the absolute, legally verifiable certainty that the metal will never, ever fail. Because if it fails, you do not just have a bad industrial accident that costs you some downtime. You have an international incident that will be taught in history and engineering books for the next century. This means, before you have generated a single watt of power, before you have sent a single utility bill to a single customer, you are buried under a mountain of debt so incredibly heavy that only a government or a heavily regulated state-backed utility monopoly can even theoretically carry it. Now, let us talk about what happens when you finally turn it on. This is where the economics of nuclear power flip completely upside down. A nuclear plant has the highest capital cost of almost any energy source on Earth, but it has incredibly low marginal operating costs. Once the plant is finally built, generating the actual electricity is absurdly cheap. The fuel is uranium. It is a globally traded commodity, but unlike coal or natural gas, you need virtually none of it to achieve massive output. A single enriched uranium pellet, the exact size of your fingertip, contains the exact same amount of energy as 1 ton of coal, 149 gallons of oil, or 17,000 cubic feet of natural gas. A standard commercial reactor only needs to be refueled once every 18 to 24 months, and even then, they only swap out about a third of the reactor core at a time. But you do not just dig uranium out of the dirt and throw it into a reactor core. It has to be mined, milled into yellow cake, converted into a gas, and sent through massive centrifuges to be enriched, which increases the concentration of the highly reactive U-235 isotope. After that, it is manufactured into precisely engineered ceramic pellets and loaded into zirconium alloy tubes to create fuel assemblies. Even with all of that incredibly complex, highly specialized processing, fuel only accounts for about 20% of a nuclear plant's operating costs. Compare that to a standard natural gas plant, where the fuel burning in the turbine makes up 70 to 80% of the operating cost. If the global price of uranium doubles tomorrow because of a geopolitical crisis, your overall operating cost barely twitches. Your fuel is essentially locked in, incredibly dense, and vastly insulated from the daily panic of global commodity markets. The problem is, the other 80%. A nuclear plant requires an absolute army to run it safely. You have hundreds of highly specialized, incredibly well-paid engineers, operators, and technicians on site 24 hours a day, 7 days a week, 365 days a year. You have heavily armed, private paramilitary security forces guarding the perimeter with tactical gear. You have continuous, grueling inspections from resident federal regulators who practically live in the control room. You are maintaining redundant safety systems for your redundant safety systems. The operations and maintenance costs run in the tens of millions of dollars a year, regardless of whether the plant is running at 100% capacity or 0% capacity. You cannot send the control room operators home or turn off the security perimeter cameras just because the market demand for electricity happens to be low today. The fixed costs are absolute. Therefore, the only possible way to make the math work is to run the plant at 100% power all day, every single day, without stopping until you literally run out of fuel. The industry calls this baseload power. A nuclear plant is a machine designed to run flat out, and in the United States, they do exactly that, achieving average capacity factors of over 92%. That is higher than natural gas, higher than coal, and vastly higher than wind or solar. It sounds incredibly efficient, and it was until the grid completely changed around it. This brings us to the fundamental problem with owning a nuclear plant today. You are selling a product that is perfectly reliable into a market that no longer values reliability the way it used to. Electricity is not like gasoline or crude oil or timber. It cannot be easily and cheaply stored on a massive scale. It has to be consumed by a house or a business the exact millisecond it is generated by your turbine. This means the wholesale price of electricity fluctuates wildly from minute to minute throughout the day, based entirely on supply and demand. On a historically hot summer afternoon, when everyone turns on their air conditioning at the same time, the grid is strained and the price per megawatt hour skyrockets. In the middle of the night in the spring, when nobody needs heating and nobody needs cooling, the price absolutely crashes. For decades, nuclear plants made a fortune selling steady baseload power into a predictable grid. But then came the American fracking boom, which flooded the domestic market with incredibly cheap natural gas. Natural gas plants are cheap to build, and more importantly, they can be turned on and off in a matter of minutes. When grid prices are high, they fire up and capture the profit. When prices are low, they simply shut down and stop burning fuel. Nuclear plants cannot do that. Changing the power output of a massive nuclear reactor, a process called load following, is technically possible, but economically ruinous and mechanically stressful on the equipment. And then came wind and solar. Renewable energy has zero fuel cost and is heavily subsidized by federal tax credits. On a beautifully sunny, highly windy spring day in places like California or Texas, millions of solar panels and thousands of wind turbines produce so much electricity that there is vastly more supply on the grid than there is demand from homes. When this happens, the wholesale price of electricity does not just drop to zero, it literally goes negative. The grid operators will charge generators money to put power onto the grid, just to prevent the physical transmission wires from overloading and causing a blackout. When prices go negative, the natural gas plants simply turn off. The wind turbines apply their brakes. The nuclear plant cannot turn off. It takes days to safely and properly power down a commercial reactor, and days to bring it back up. A complex process that involves intense regulatory scrutiny and highly complex physics regarding the buildup of neutron-absorbing xenon gas inside the reactor core. So the nuclear plant just stays on. It keeps churning out perfectly clean, perfectly reliable baseload power, and the owner literally pays the grid operators to take it. You are operating a multi-billion-dollar technological marvel, staffed by literal nuclear physicists, and you are losing money on every single electron you produce, because the wind happens to be blowing particularly hard that morning. You are the ultimate victim of the duck curve, the industry term for the extreme swings in net load caused by renewable generation. This specific market dynamic has pushed dozens of perfectly functional, perfectly safe nuclear plants in competitive markets to the absolute brink of bankruptcy over the last decade. It has forced state governments in places like Illinois and New York to step in with massive, billion-dollar zero-emission credit subsidies just to keep the plants open so they do not lose their largest sources of carbon-free energy. Now let us talk about what happens at the end. Because the economics of owning a nuclear plant do not neatly stop when you stop generating electricity. Every single day your plant operates, it is creating high-level radioactive waste. Spent nuclear fuel. It is highly radioactive, it is thermally hot, and it will remain dangerous to human biology for tens of thousands of years. When the commercial nuclear industry started in the mid-20th century, the ironclad promise was that the federal government would build a permanent, deep geological repository to take this waste off the hands of the commercial operators. That was supposed to be Yucca Mountain in the Nevada desert. But after decades of vicious political warfare, endless lawsuits, and billions of dollars spent, the Yucca Mountain project was functionally abandoned. The federal government breached its legal contract to take the waste. So where does it go? Nowhere. It stays exactly where you made it. When the spent fuel rods come out of the reactor, they are placed in deep pools of circulating water for several years to cool down thermally and radiologically. Once they are cool enough, they are transferred into dry casks. These are massive, 20-foot tall cylinders of specialized steel and concrete, weighing well over 100 tons each. They sit on a highly secure concrete pad right outside your reactor building. You, the plant owner, are responsible for guarding them, monitoring them, and maintaining them indefinitely. You have effectively become a permanent, de facto high-level nuclear waste storage facility, a job you never actually signed up for, and a liability you never wanted. The federal government does pay out ongoing financial settlements from a mechanism called the Judgment Fund to cover your storage costs because of their failure to open a national repository. But the physical liability, the optics, and the risk are still sitting squarely on your property. And then there is the end of the plant's actual life. A nuclear reactor is initially licensed by the NRC to operate for 40 years, which is often extended to 60 or even 80 years if the metallurgy holds up. But eventually, the relentless neutron bombardment embrittles the steel pressure vessel, the thousands of miles of wiring degrade, the components age beyond repair, and the plant must be permanently shut down. You cannot just lock the chain link fence, turn off the lights, and walk away. You have to actively decommission it. Decommissioning a nuclear power plant takes decades and costs roughly $1 billion per reactor. You have to safely and methodically dismantle a building where the concrete and steel themselves have become physically radioactive. You have to cut up the massive reactor pressure vessel underwater using highly specialized remote-controlled robots. You have to load and ship thousands of tons of low-level radioactive debris to specialized, highly regulated disposal sites in the desert. Federal law strictly requires plant owners to set aside money in a dedicated decommissioning trust fund over the entire operating life of the plant, skimming a little bit of profit off the top every single year and investing it in the market to ensure the $1 billion is there when the time finally comes. But if the stock market crashes or the decommissioning process runs wildly over budget, as it often does, the financial liability falls right back onto the operator. It is a business where the exit cost to tear down the building is higher than the startup cost to build almost any other normal industrial company on Earth. This is the absolute paradox of the modern nuclear economy. If we are actually going to decarbonize the global energy grid, if we are going to power the massive new artificial intelligence data centers that major technology companies are building at a breakneck pace, wind and solar alone are not going to be enough. We need firm, dispatchable, zero-carbon baseload power that operates flawlessly regardless of the weather. Nuclear is the only proven technology on Earth that can actually do that at a massive commercial scale. Everyone who looks at grid math knows we need it. Tech billionaires are currently pouring billions of dollars into advanced reactor startups. Microsoft just signed an unprecedented 20-year deal to literally restart the dormant 3 Mile Island Unit 1 reactor simply to secure enough reliable power for their AI ambitions. Amazon is buying entire data center campuses directly attached to the Susquehanna nuclear plant in Pennsylvania just to get direct access to the atoms. The legacy industry is currently placing all of its future hope in SMRs, small modular reactors. The fundamental idea is to stop building massive, bespoke, custom-engineered concrete fortresses that take 15 years to construct and bankrupt the utilities that order them. Instead, the plan is to build smaller, highly standardized reactors in a centralized factory. Ship them on a standard flatbed truck or a freight train, assemble them quickly on site, and scale them up by linking them together as demand grows. Mass production instead of endless mega projects. It is a brilliant engineering concept that theoretically solves the massive upfront capital cost problem that killed the previous generation of plants. But as of right now, not a single commercial SMR has been built and operated in the United States. The leading company in the American SMR space recently had to cancel its flagship project in Idaho because inflation, interest rates, and severe supply chain issues pushed the estimated cost of the power so high that the local municipal utilities could no longer afford to accept it. The economy of owning a nuclear plant is a story of incredible, borderline miraculous physics trapped inside an impossible, unforgiving market. You are dealing with regulatory hurdles that literally measure time in decades. You are building infrastructure that costs tens of billions of dollars before it generates a single cent of revenue. You are operating a machine that must run flawlessly all day, every day, regardless of whether the wholesale market actually wants to pay you for your product at that exact moment. And your physical and financial liability easily outlives you, your children, and quite possibly the nation that originally issued your operating license. It is the most impressive, most reliable, most environmentally necessary machine humanity has ever built. And right now, almost nobody can afford to own one. If you found this video valuable, leave a like, subscribe, and comment below which business you want me to cover next.